Okay, so this lesson is going to be on Gibbs energy graphs. So we all know already that if you want to work out the Gibbs energy equation, or Gibbs energy, it's delta G equals delta H minus T delta S. What we're going to be looking at in this little bit is how this formula can be written as or can be matched to the equation for a straight line graph. So you should know that the equation for a straight line graph is y equals mx plus c. You should know that from GCSE. You're probably thinking already, oh my goodness, I didn't sign up for this. I thought I'd left these behind me. But y equals mx plus c, where we know that y is what you plot on the y-axis, x is what you plot on the x-axis for a graph, m will be the gradient of the graph, and c will be the y-intercept of the graph. I'm going to rearrange this equation now to fit that. You'll notice that you've got two things multiplied together, two terms multiplied together. They're going to go at the front. They're going to become my mx. So delta G equals, but notice what I do, minus delta ST plus delta H. They've been swapped around, but this is the form that we're going to be using to plot these graphs. So what we're going to do then, we're going to plot a graph where the y-axis is going to be delta G, the x-axis is going to be temperature, so it's going to be a temperature against delta G graph, and if we plot that, the gradient of your graph will give you minus delta x. That's going to annoy some of you later because you've got to flip the sign on it. And the y-intercept will give you delta H. Alright, it's going to sound like it's going to be a complicated lesson, but it's not necessarily going to be a complicated lesson. A little recap then. When we're just dealing with delta G, there are 4 different scenarios that we would expect. Let me just remind you of these because there are going to be 4 graphs, you see. I'm going to write delta G equals delta H minus T delta S. I'm going to write it like this just to remind you. We can have this situation where you have an exothermic reaction that creates disorder. So we can have a negative value for delta H and a positive value for T delta S. I hope you remember from previous lessons that this is an example of a reaction that happens or is feasible at all temperatures. You okay with that? Good. Then we can have an endothermic reaction that creates order. And as we've seen in previous lessons, that can't happen or is unfeasible at all temperatures. Then we can have a plus-plus situation, endo creating disorder, and we can have a minus situation, exo creating order. And these are my temperature dependent reactions. They become feasible at a special temperature. So if you're watching this as a standalone video, it's not going to make much sense unless you've done a bit of delta G before. We know that a plus-plus situation will happen above a certain temperature, and we know that a minus situation will happen below a certain temperature. So that's something that I would expect you to have that knowledge now. And what we're going to look at is how graphs can show this. All right? So there are going to be 4 graphs that are going to be straight line graphs that will explain this situation beautifully. All right, turn over your pages or get a nice clean sheet of paper. I'm going to draw 4 axes. Now, have I got a ruler? I've got so very much. So, there are going to be 4 graphs, and I'm going to put 2 side by side. So they are going to go to minus values. I'll show you how to label them in a sec. These are going to be our delta G against temperature graphs. I'm just going to quickly label these up once I've returned this ruler. Okay, so if you missed this lesson because you're falling, you're catching up these notes, please. Okay, so each of these is a delta G graph. I'm going to write the rearranged equation up here. Delta G equals minus delta ST plus delta H, to remind you of that line of equation for a straight line. So the y-axis is delta G. So we're going to label that as delta G. And this is 0 on that axis. And the x-axis is T in Kelvin. So that's down here is absolute 0 Kelvin. So I'm going to do this on all of my graphs. There's delta G is 0, temperature in Kelvin. Delta G is 0, temperature in Kelvin. Delta G is 0, temperature in Kelvin. All right. So, in each of these graphs, we are going to draw a straight line that represents an experiment where delta G values were measured against temperature and then they've been extrapolated back to 0. So, the first line we're going to draw, actually the first thing I want to say, if you have a look at this graph, here is delta G, and the very important thing to remember is when delta G is less than or equal to 0, the reaction is feasible. Do you all remember that fact? So, there's 0, so this is minus numbers for delta G. What that means is, this section of the graph here, now if you had a green pencil, that would be quite nice, because this means the reaction will go, or it'll be feasible if it's down here. And at the top, if the graph ends up in the top bit of that, I'm going to borrow a red pen here. So this part of the graph is not feasible. Now, of course, they won't be coloured in real life. This is just for the visuals, for the teaching purposes of it. No, I don't have a green pencil, but somebody might. Green pen, let's shoot some lines on there. So I'm going to do these green. Hopefully it doesn't distract this. Oh, pardon, my voice is gone. Hopefully it doesn't distract from the information we're going to put on it. My voice is crap. Right, okay, so bottom part of this graph is basically where it becomes feasible, and if delta G goes above 0, it's going to be unfeasible. So the first situation I'm going to do is I'm going to draw this line graph on here. I'm going to start at a value that is below 0, and I'm going to draw a line that goes like that. Alright. This is the first type of graph to discuss, is one that starts below 0 and goes more negative. The second type of line we'll discuss is one that starts above 0 and gets more positive or less feasible. You might already see where these things are going. You might not. Then I'm going to do one that starts above 0 but then ends up below 0. Almost looks like that's one that gets feasible above a certain temperature. And then the opposite will be starting below and going up. 4 different scenarios. Okay, and we just have to unpick which one is which. So, what we've got here, if I'm looking at scenario number 1, delta H. Now, delta H, if we look at our rearrangement, delta H is just the y-intercept. So all you do is you look here and you read this number off in the exam. So if that's like minus 153, that's delta H. You don't have to do anything with it. There's your delta H value. So we are dealing here with delta H that is a negative value. This is an exothermic reaction. I've written there delta H negative exothermic. You just read delta H off that axis. It's that straightforward in the exam. This is the y-intercept. It's in kilojoules per mole because delta G is in kilojoules per mole. The next thing I want to do, if I want to work out what delta S is, here's the process you go through. It's very straightforward. I can see that this is a negative gradient. So what do I know? The gradient is minus delta S. That's what it tells me up here. Look, the gradient is minus delta S. this gradient is negative. That's a negative gradient. Therefore, delta S is positive. You heard that overwhelming response there. Everybody shouted out positive. So, delta S is positive. It creates disorder, or disorder increases. This is a graph that shows an exothermic reaction that creates disorder. And whoa, I don't know what that noise was. Wow, that was a better noise. It's always feasible. Whoa, what are you laughing at, Ben? Big Ben got a name check, it'll be made up. That is now eternally going to be on YouTube. This gradient is negative at all values. Now, some students in the past have said, yeah, but what if you continue cooling it down? You can't, because that's absolute zero. All right. So these would have come from experimental data that looks like that. They'll have drawn a line of best fit and extrapolated this last bit back to zero, so you can read off delta H. Okay, going to speed up now. Do you get the idea with these? Okay. Second situation then. Delta H. What can you tell me about delta H? It's positive, yeah, because I don't know, that reads plus 302 or whatever it might be. It's positive. This is a positive value. This is an endothermic reaction. Right, what do I know? This is the process I'm going to. Gradient equals minus delta S. This gradient is positive. Therefore, delta S is negative. Sorry, you can't read me writing, but deal with it. Delta S, negative. The disorder decreases. That's what a graph looks like for an endothermic reaction where the disorder decreases. What can you tell me about the feasibility for a reaction like this by looking at that graph? Not feasible at any temperature. You cannot do anything to this in terms of temperature to get it below that line. This reaction will never happen. Okay with that? The last two situations are ones that cross the line. What I would like you to decide, please, is which one of these is a negative minus a negative, and which one of these is a positive minus a positive, please. It should be very sort of straightforward and quick to do. Just preparing by writing delta H and delta S. Okay, I've got 4 minutes left to record this before the lesson finishes. I've been very efficient. Okay, looking at the first one, I would ask for feedback because I'm recording it. I'm just going to sort of do it. Right, delta H is positive, so this is an endothermic reaction with a positive delta H. The gradient is negative, therefore delta S is positive. So that's delta S is positive, so we're increasing disorder. So in this situation, what is the significance of this temperature? Oh yeah, I wasn't going to ask for feedback, was I, because I'm recording? Oh yeah. So you can see from the graph that at this temperature and above this temperature, the reaction is feasible. The reaction is feasible at and above this temperature. You know, we saw it goes into the green region. Next one then, we've got a negative value down here, so delta H is negative. This is an exothermic reaction. The gradient is positive. We know that gradient is minus delta S, so that means delta S is negative. You made a mistake there. Disorder decreases. Significance of this temperature. You can either say the reaction is feasible at and below, or it is unfeasible above. So this is feasible at and below this temperature. So it's feasible in this region. Right, I was very rushed, but I'm going to just show you now an example of how this looks in an exam. 2 minutes left. So if you're poorly at home, and I know a few of you are off today, I hope you get better soon. So this is what you've missed. Here is a delta G graph. It's for the reaction of nitrogen and hydrogen to make ammonia. Just going to zoom in a couple more clips. There we go. It said write an equation to the relationship between them. That's very straightforward. Right, before we look at any of the questions, we can already see. So I'm going to ask the class to discuss this. Is this an exothermic or endothermic reaction, please? All right, they're all gone exothermic. If you extrapolate this back to the axis, you will get a negative value down here. So delta H is negative. It's an exothermic reaction. This question then goes on to say, what is the value of the slope? So it asks you to calculate the value of the slope. So I would draw some lines like that. I would work out the y and the x. I would divide y by x. This is a positive gradient. It's a positive gradient. So delta S is negative. Okay? That's all that means. In this question, they say, what's the value of the slope? You would do the y divided by the x. The units of the slope in this case would be kilojoules per mole divided by Kelvin. So kilojoules per mole per Kelvin. And the symbol for the slope is minus delta S. That's what this is. All right. I'm just going to show you another thing in case you're off. This is what a 7 marker on it looks like. This is a table of temperature against delta G. And they ask you to plot the graph. So it's not very well printed here, but you have to plot the delta G against the temperature. And let's just say you got values that look like this, which you sort of do. You would plot these. And then it says, can you work out delta S from that? So here's the process you would go through. You get 2 marks for plotting it and drawing a line of best fit. You would then draw yourself a nice big triangle to work out the gradient from. The bigger the triangle, the better, the more precise. You would work out Y, you would work out X. 1 second. If you did Y divided by X, that would be kilojoules per mole divided by Kelvin. That's good, you've got yourself some marks. It then wants you to say what delta S is. So say, for example, and this is the actual number, if you do kilojoules per mole divided by Kelvin, you get this value of 0.17 for the gradient. That means that delta S would be minus 0.17 kilojoules per mole. So remember the gradient is minus delta S. And they want it in joules per mole per Kelvin, so you would then have to times by 1,000. That bit was very, very quick. You're going to get these questions. You have to do them before next week. Everybody in the class all right with that? We're going to practice these next lesson. Goodbye. Anyone want to say bye? See ya. Bye. 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 Bye.